Welcome to lecture 20. In this lecture, we're going to talk about set associative caches. So we have homework due today and project 3 will be due on Thursday. As many of you would have noticed, we changed the grading policy to account for the issues we faced in the midterm. So I have the link on the slide. In case if you have not gone through that policy, please do so. And if you have any questions, please feel free to contact me or any one of the staff members. So before we can understand set associative caches, let's briefly review the main ideas we have talked about so far. First, we started off with a very simple cache organization where we had the address stored with the data. And then we said, well, that's too expensive because for every 1 byte of data, I need to store the full address. And so therefore the cache overhead was prohibitive. And the way we solved this problem was by increasing the size of the data that is stored per tag. And we called this the cache block. And so now you need to have only 1 tag per cache block as opposed to 1 tag per byte. And that significantly reduced the tag overhead. Now, when you are given an address, we would break this address, we as in the cache would break this address into 2 parts. The one that contains the block offset, which is defined by the log to the base 2 of the number of bytes in the block. So in this case, there are 2 bytes in the block, so therefore we have 1 bit. And then whatever remains in the address would be the tag. So in this case, it's a 4-bit memory that we are assuming, and therefore we have 4 bits. So 4-bit minus 1 is 3 bits. And those 3 bits are physically stored as part of the tag in the cache. Now, if you want to access this cache, you take the address. The cache would divide that into 2 parts, like I said. And then the tag would be compared against all the tags that are stored in the cache. And so if any one of them found a match with the given tag address, then we would declare a cache hit. And it is also important that when the tag matches, the valid bit corresponding to that cache line is set, because we don't want to be accessing an invalid cache line which has been evicted before, or maybe we are just starting off the program, so the valid bit is not set. So the most important thing here to understand is the given tag is compared to all the tags in the tag array. Now the problem with this approach is that the number of comparisons that you need to make is too many. Even though you can do it in parallel, the hardware would require significant number of comparators to accomplish this job. So in order to reduce the cache overhead of performing these many comparisons in parallel, we then talked about an idea called the direct mapped cache. We said, well, the problem is, given an address, I need to go and compare all these tags, and that is too expensive. So how about I reduce the number of possibilities by saying a given cache block can be mapped to exactly 1 cache line in the cache. So the way we accomplished that was by taking the address. We can't really do anything with the block offset, so that's gone. And we grab the remaining least significant bits, as many as we need, to create an index into the cache. So we treated the set of cache lines like we would treat an array in a normal C program. And then we created an index to access that array of cache lines simply by constructing an index out of the least significant bits in the remaining part of the address after leaving out the block offset. So in this example, I have 4 cache lines. So we need 2 bits to index into this array of 4. So then we chose a line index of size 2 bits. Now the advantage of this cache is, of course, given a cache line index, there is exactly one cache line where this particular address can be stored in. And therefore, at runtime, one has to only check the tag that corresponds to that cache line. And therefore, with just one comparison, one can declare whether it is a cache hit or a miss. Okay, let's look at the dynamics of how a direct mapped cache would work. So given an address, the cache would break it into 3 parts as opposed to 2 in the case of fully associative cache. We now have this line index. Now the line index would be used to decode, and it's decoded, and then it selects exactly one position in the tag array, and then a given tag would compare to that tag, exactly one comparison, and if it is a hit, then the data corresponding to that cache line would be obtained, and then the block offset would then select the necessary part of that cache block. So if the block offset is 0, you grab the 0th byte. If the block offset is 1, you grab the first byte, and so on. So now let's talk about another extension to this cache architecture, which is called as a set associative caches. Now if you go back to this direct mapped cache design, this is really good in terms of reducing the overhead of comparisons, which in turn helps reduce the cache latency. But the downside is it's too restrictive in terms of where a given cache block can be placed in. So in this case, there is exactly one place in the cache where I can store it. And now the problem is this can lead to poor cache miss rate, because imagine, for example, that the program happens to access just 2 cache blocks, the ones that I am marking on the slide here. Unfortunately, they both happen to map to the same cache line. And so they would repeatedly thrash each other and evict each other out of the cache. And so you have a pattern, let's say like AB, 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 where A refers to this cache block over here and B refers to this cache block over here. Now you would end up with a cache hit rate of 0, and that's not really good in terms of cache performance, because you really have extra cache capacity. So it's certainly not because you didn't have cache capacity that you ended up with the 0% cache hit rate. It's really because of the cache organization, where we ended up mapping 2 cache lines that are frequently accessed to the same place in the cache. So is there a middle ground where we avoid the overhead of tag comparisons in the case of fully associative cache, but at the same time we enjoy a little bit more freedom than direct mapped cache? What is a set associative cache? Well, to explain that, let me first start with the direct mapped cache. So what I'm showing in this picture is a direct mapped cache with the 4 cache lines. And like we said, a direct mapped cache is too restrictive because a given cache block can be mapped to exactly one cache line. And that's a problem, because when you have a program that happens to access the cache blocks that get mapped to the same cache line, then you may end up with a poor cache performance. So for example, in this case, if these 2 are blocks A and B, and if your program accesses A and B alternatively, then you may end up with a cache performance that is very poor. In fact, it's 0 cache hit rate. So we want to create more choice. How do we do that? So let me do the following. So obviously I need more choice. So the way I'm going to do it is I'm going to create what is called as a way. So I'm going to call this as a way 0, what I originally had. And I'm going to take the same cache lines that I had before. Keep in mind that I'm trying to create a different cache organization, but I don't want to increase the cache size. So I had 4 cache lines before. I still have 4 cache lines now, but I have reorganized them. The main change now is that I only have 2 rows as opposed to 4 I had before. So instead of 2 bits, now I need only 1 bit to select my row. So before the row had only 1 cache line, but now it has 2. So therefore, a given address now can be stored in any one of these 2 cache lines that are part of that row. I'm going to call this row as a set. So a set is nothing but a set. A cache set is nothing but a set of cache blocks that are that are indexed with, that share the same index. Okay. Now the color of these need to be changed because the line index for the cache block that is stored in this cache block is going to be same as the cache block that is going to be as the line index of the cache block that is going to be stored in this cache line, right? So what you actually have is 2 sets of cache lines, 2 cache lines that are part of the same cache set. So now I have set 0, set 1. I no longer have set 2 and 3 because we used up those cache lines and added them to the sets 0 and 1. So now if you look at this picture here, it's still the same number of cache blocks like we had before, but they're reorganized in a different way. Now if I have a cache block, let's say A and B, right, they're still mapped to exactly 1 cache set, but fortunately that cache set has 2 cache lines, which means that now I could store a given cache block in either of those 2 cache lines. So I could store A here or I could store A here, which means at any given time it's possible to store both A and B together in the cache. And that way the pathological example that we had before, where the program happens to access the cache blocks A and B alternatively, would actually enjoy a very high cache hit rate, close to 100% in the steady state. So now I have 2 cache sets, 0 and 1, and we have 2 ways, way 0 and way 1, and that's why it's a 2-way set associative cache, and a given cache block can be stored in any one of the 2 ways depending on which one is free. How do you know which one is free? Well, this goes back to our discussion on replacement policies and how we handled it in the case of fully associative cache. And so remember that we talked about a policy called LRU, the least recently used policy. So in case of both cache lines are occupied by some cache blocks, and if a new cache block comes around and happens to map to the same cache, the cache set, which is not true in this example, but assume that A, B, and C all map to the same cache set. Now you have to find a victim and evict it. And the way we would find that victim is by using a replacement policy. And if you use LRU policy, then you will check to see if this is the least recently used or if this is least recently used, and depending on which one was least recently used, you would choose that as a victim. So essentially all the ideas we talked about in the case of fully associative cache, the replacement policy, those are applied within the blocks of a set. Of course, across the sets, they don't have any impact. So for example, I may have C and D, and between A, B, C, D, it may be the case that C is the least recently used, but that doesn't matter, because if I have a new block that needs to be stored in the set 0, my choices are just A and B. C and D are not my choices, and therefore it doesn't matter what their LRU rank is. So here's another way to visualize the same cache organization. So this is still a two-way set associative cache with two sets, and because it has only two sets, I have only one bit that I need for accessing, for figuring out which set I should be accessing. And within that set, I have two cache blocks that belong to two different ways. And I have the freedom to store my cache block in any one of those two ways, depending on which one is available. Just like in the case of a direct mapped cache, some portion of my address is being used for the set index, and the remaining would be used up by the tag. And the tag is stored along with the data as shown in the picture. So here is yet another way to visualize the set associative cache. So given an address, I would first compute, I as in the cache would compute the set index, and that would depend on how many sets I have in the cache, and we'll talk about that in a moment. So I take the set index and access the particular row, which is essentially the cache set. And unlike in the direct mapped cache where I need to only make one comparison, here I need to make as many comparisons as there are number of ways. So in this example, I have two ways, so I need to compare the given tag to the tags stored in both of the ways. And if any one of them matches, then I can declare a hit. And once I know which tag matched, then I can retrieve the data from the corresponding way, right? So if this tag matched, then I should be getting the data from the corresponding way from the data array. And then I will subselect furthermore the particular byte in that block depending on the block offset, just like what we did in the case of the direct mapped cache. So let's synthesize these three cache organizations into one slide and see if we can make sense out of it. So again, we started off with this idea of a fully associative cache where all the cache blocks were essentially part of the same set, right? So that's one way to think about it, because if I have to bring in a cache block from memory, in the case of a fully associative cache, I can place it anywhere I want. So that means the whole cache is one single set. And that's what is represented here. So if I have a cache with space for 4 cache lines, and they would be organized such that there is exactly one cache set. Let me call it as a cache set 0, right? And so another way to think about it is this is just one row. And so if you're going to have only one row, you don't really need a line index. So as a result, your address is interpreted as only two parts. One is the block offset and the other is the tag. And the reason why the set index is absent in this case is because it has 0 bits. Because if I have only one set, I don't need a bit to tell me which set to access. Now for the same cache size, we talked about how to construct a direct mapped cache. In this case, we went to the other extreme and said every cache block is part of its own set. So in this case, we have 4 cache sets effectively, cache sets 0, 1, 2, and 3. And each cache set had exactly one cache block, or rather one cache line, right? And these two are 2 bytes that are part of the same cache block. So I have 4 cache sets, which means that my address will have the block offset, and it should have 2 bits to select my cache set, and the remaining would be my tag. Now, what we talked about just now is a 2-way set associative cache where we reorganized it so that each row now had 2 cache lines, or each cache set now had 2 cache lines. So now I have 2 cache sets, cache set 0 and set 1, right? Because total number of cache lines is 4, and I'm organizing them in 2 sets, so therefore each set will have 2 cache lines. So now in order to select the cache set, I don't need 2 bits anymore. A single bit would do. So that's exactly what I would have in this case. Okay, so all of these ideas are consistent with each other, as you can see. I mean, one way to think about a fully associative cache is, oh, I had 4 blocks in the set, so I could even say this is a 4-way set associative cache. I had only 4 cache lines, and therefore I could have only 1 cache set, but that's another way to think about it, right? And if I had a cache of size 8, and if it was a fully associative cache, then there would be 8 cache blocks that are part of the same set. Then if I have to phrase it as a set associative cache, I have to call it as a 8-way set associative cache. That's just another way to think about a fully associative cache. And the trade-off here is, in the case of fully associative cache, I need to make 4 tag comparisons, and that is expensive. In the case of a direct mapped cache, I just need to make 1 tag comparisons. That is much more faster, but the problem is it restricts my choice, and that can result in poor cache hit rate. In the case of 2-way set associative cache, it's somewhat flexible compared to direct mapped cache, but not as flexible as a fully associative cache. And so the cache miss rate can be higher than that of fully associative cache. So the cache miss rate would be the best for the fully associative cache. It will be okay for the set associative cache, and probably the worst for the direct mapped cache. So let me go through a few equations which are very useful when you are solving cache problems. It's important that you familiarize yourself with these equations. So we have a cache size which is typically given to you, and you take the block size, and if you divide cache size by the block size, you will know the number of cache blocks that you can store in the cache. Sometimes we refer to the cache blocks as cache lines, but the technical difference really is that cache line, think of it as a hardware physical structure that has space to store the cache block, and along with some metadata such as tag, LRU bits, valid bit, and so on. So a cache line is cache block along with that metadata. But the cache lines, the number of cache lines is going to be exactly same as the number of cache blocks for any problem. And then you have the block offset size. Now this is important when you want to interpret a given address. So if you're given an address of size whatever, let's say 32 bits, the block offset is the last few bits, and the number of bits you would use for the block offset obviously depends on the block size. So if you take the log to the base 2 of block size, you will be able to figure out how many bits you need for the block offset. In the case of a fully associative cache, everything that remains would be a tag. But in the case of let's say direct mapped cache, the number of sets that we have is going to be dependent on how many lines there are. Now number of lines is same as the number of cache blocks, which you would have computed using this equation. So the number of cache lines divided by 1. So why is it 1? Because the number of ways is 1 in the case of a direct mapped cache. So we are saying that the number of sets is exactly same as the number of lines, because each set has exactly 1 line, right? And then if you have a 2-way set associative cache, you take those cache lines and you partition them into 2 ways, and so the number of sets would be half of the number of lines. And in the case of n-way set associative cache, you are partitioning the given set of cache lines into n ways, and so every set would only have number of lines divided by n. In the case of a fully associative cache, you place all the cache lines into one set, and therefore the number of sets is going to be 1. So n is equal to the number of lines. And now if you have computed the number of sets, then you can figure out the number of bits that you need for the set index as simply log to the base 2 of number of sets, and then you would have figured out your set index, part of your address. And then the remaining part of your address is what you would use as a tag. So the tag size would be the given address size. In our example, it is 32 bits, we said. And then you take away the set index and you take away the block offset. What you are left with is your tag. Now, all this computation of partitioning the address into these 3 parts, it's specific to a cache design. It's nothing to do with the ISA at all, except for this address size specification. So the only thing your ISA defines is the address size. The set index, block offset, etc., they're all specific to the cache design, and therefore they are hidden from the programmer and the compiler and so on, like we talked about a few lectures ago. Now let's use these equations to solve a very simple problem. So you're given a 32-bit ISA, and the cache size is 16 kilobytes, and the cache block size is 64 bytes. And so the number of lines would be the cache size, which is 16 kilobytes divided by 64 bytes. And so when we say kilo in the case of cache problems, we are always talking about 1024, not 1000. And so if you do the math, so kilo is going to be 2 to the power of 10 divided by 2 to the power of 6. So that would be, so we can express this as 2 to the power of 4. And so that's 14 minus 6, that is 2 to the power of 8, which is 256. So the number of cache lines is going to be 256. And then the number of bits that we need in the block offset. So the block offset size is going to be log of 64, which is 6 bits. So now in the case of a fully associative cache, keep in mind that we don't have a set index. And the reason why we don't have a set index is because we have only one set. So you don't need an index to select that set. So as a result, you have only the block offset, which we just computed it to be 6 bits. And then the remaining is going to be the tag. So the total address size is going to be 32 bits because the ISA that we are asked to assume is a 32-bit ISA. So therefore the tag size is going to be 32 bits minus the block offset. So that is 32 minus 6, which is 26. Then we have direct mapped cache, where we have to now figure out what is the size of the set index going to be. So the block offset remains the same, but to compute the set index, we need to compute the number of sets, because we know that the set index size is nothing but log of the number of sets. How many sets do we have? Well, in the case of a direct mapped cache, the number of sets is same as the number of lines, because the number of ways happens to be 1 in the case of a direct mapped cache. So that is 256. So therefore the set index is going to be log to the base 2 of 256, which is going to be 8 bits. So we have 8 bits for the set index, and this is your block offset. And the number of bits for the address does not change across the cache architectures. It's an ISA specification, not a cache specification. So that remains to be 32 bits. So it's 32 minus 8 minus 6, which is 32 minus 14, which would be 18 bits. And so finally we have 4-way set associative cache. So in this case, what's going to change is the number of sets. So the number of sets is going to be now number of lines, and we are going to divide those lines into 4 ways instead of single way like we had for the direct mapped cache. So number of lines is 256 divided by 4, that is 64 sets, which means your set index size is now log to the base 2 of 64, and that is going to be 6 bits. And so the address size again doesn't change. The block offset also doesn't change because we are asked to assume the same block size for all of these problems. So that remains to be 6 bits. And then we just computed that the set index is 6 bits. And so whatever that remains is going to be the tag. So that is 32 minus 6 minus 6. So that is going to be 20 bits. Okay, let me illustrate the function of a set associative cache using a very simple example. So we have a sequence of instructions on the left hand side, and we have the same 4-bit memory that we have been using in our examples. And we have the cache in the middle. So we are going to assume that this is a write back cache, and we are going to allocate a cache block in the cache when there is a write to an address that is not there. So therefore it's write back and write allocate. So now we have 4 cache lines, and we are going to assume that it is a 2-way set associative cache. What that means is each set has 2 cache lines, so they are color coded. So you can see that there are 2 colors for the cache, and each one corresponds to a different cache set. And the way that we are going to identify the cache set for an address is using 1 bit, because we have only 2 cache sets, so we just need 1 bit in the address to figure out which set a particular cache block should go to. So what I have done on the right hand side of the slide is taken the addresses from 0 to 15 and partitioned them into these 3 components. So the block offset is easy to understand. We have 2-byte blocks, so therefore we need only 1 bit. So the last bit is for the block offset. We're not really going to use it much in this example. The next bit is the set index bit. Like I said, we have 2 cache sets, and therefore we need 1 set index bit. And the remaining is going to be a tag. And because it's a 4-bit ISA that we are assuming, we have 2 bits for the tag. Alright, so now let me go ahead and simulate the 6 instructions that we have on the left side and see how this would function. So the initial state is that the cache is empty, so all the valid bits are set to 0. Now I have my first reference to address 1, and address 1 has an index 0, which means I'm going to be accessing the set 0. And I'm going to check the tag. Well, the tag doesn't match, and the valid bit is also not set, so clearly this is a cache miss, and I have to bring in this cache block into the cache, and I would store it. That's exactly what I did. And so we have to also keep track of the LRU now. So in the case of a direct mapped cache, we didn't have to bother with the LRU policy, because for every cache block there was exactly 1 cache line that could store it. So if it was a cache miss and we have to bring that cache line into the cache block, bring that cache block into the cache, then we have to evict whatever that was there before. So there was no choice that the cache has to make. Whereas in the case of a set associative cache, we have several choices depending upon the number of ways. So in the case of a 2-way set associative cache, we have 2 cache blocks within a set, and therefore we could evict either one of them if we need to make space. So we need to now keep track of the LRU bit for this cache. Alright, so now let's go ahead with the next cache access to address 5. So for address 5, my cache index is going to be again 0, which means I'm going to be accessing the same cache set as before. But fortunately, I do have space, so nothing to be evicted. I would simply have to bring in this cache block. So the tag was 145, and that is exactly what we would like. And notice that the valid bits have been set to 1 because they are storing valid data. Now when we try to store to address 7, it maps to the cache set 1. So this is for the first time we are going to use cache set 1, and nothing is there in the cache, and because we are using a write allocate policy, we are going to bring the cache block and store it in the cache. And we have two choices. We could have stored it in the second way as well, but we chose to do it in the first one in this example. You notice that we have set the dirty bit to 1. Remember that the dirty bit is used for implementing write back caches, where the stores modify the local cache value, and when the block gets evicted, if the dirty bit is set, then you would write back. So because we just modified that data, we are going to set the dirty bit to 1. Alright, so now let's execute my fourth instruction, which is a store to address 4, which is going to map to my cache set 0. So now I have to compare with two tags. So I'm going to compare the tag 01 with the way 0 and as well as way 1, and I discover that I have the tag in my cache, and therefore it is going to be a cache hit, and which means that I know I don't have to evict any block because I already have the cache block that I need. I just need to modify it, and when I do the modification, I would change the dirty bit, because previously I had just loaded it, but now I have stored to this block, and therefore I need to modify the valid bit. So we have had our first hit so far, and recollect why we had a hit to this address. We have never accessed this particular address before, but still it turned out to be a hit, and the reason for that was is 4 and 5 are part of the same cache block. So when we accessed 5, we brought in the address 4 as well, and this is where larger cache blocks help exploit spatial locality. Okay, now I have my instruction that loads from address 0. So address 0 has a block offset of 0, and which we don't really care, but the set index is also 0, so I'm going to access the cache set 0. The tag is 0. I'm going to compare with this tag, and I'll discover that, okay, this is a cache hit, which is great. So this would turn out to be a cache hit as well, and nothing else to be done, because the dirty bit need not be modified, because this is a load that doesn't change the state of the cache block. And then I finally have the load to the address 8, which is also going to map to the cache set 0. It has a tag of value 10, which in binary stands for a decimal value of 2. Now I'm going to compare that to tag 0 and 1. Neither of them matches, so therefore it is a cache miss. So now I have to find a victim, and remember, the way I'm going to find a victim is by using the LRU policy, but that LRU policy is going to be used only within the cache set. And so I've been diligently maintaining the LRU bit for between these two cache lines. And so I know that this is going to be my LRU cache line, so I need to evict it. And so when I evict it, I have to check the dirty bit, and because it is set, I need to write back. So I would have to write back to the memory and bring in this new cache block, and then I would have finished my cache simulation. So what are the reasons for cache misses? It's worthwhile to understand these reasons, because that can help us redesign the cache and improve performance. So there are 3 types of cache misses. The first one is called the compulsory miss. So imagine you're starting a program. Your processor and its cache is going to be initialized to an empty state. So your cache is empty. So when a program accesses an address X, let's say, for the first time, it is guaranteed to miss the cache, because this is the first time I'm accessing a cache block, and there's no way that I would have brought that particular cache block from the main memory. And so the miss that is due to the fact that I'm accessing the cache block for the first time is called the compulsory miss. Now, if I want to reduce the number of compulsory misses, then what can I do? Well, recollect what we talked about spatial locality, where we said if I'm going to access an address X, then I'm more likely to access addresses that are close to it. So now address X plus 1, I may not have ever accessed it in the past, but it's possible to turn this memory access to address X plus 1 into a cache hit if I place X plus 1 and X in the same cache block. So by increasing the size of your cache block, you can reduce the number of compulsory misses. The second type of cache miss is due to smaller cache capacity. So if I didn't have a large enough cache, then I could have cache misses. So for example, if I accessed a location X and then I accessed a number of other locations and then I ended up filling up my cache, and now I no longer have space for more cache blocks and I keep accessing more cache blocks. So now those cache blocks, if I bring it into the cache, is going to evict the one that contains the address X. So later when I access the same address X, I may encounter a miss. This miss is called the capacity miss, because if I had a cache that was large enough to store all these cache blocks, then I could have avoided this cache miss. So the way to reason about a cache miss and understand whether it is a capacity miss or not is by asking this question: would this cache miss would have occurred in a cache with infinite size but with the same cache block size, right? So you would have to go and simulate an infinite cache and then see whether for this particular address pattern, if memory access would be a hit or a miss. If the answer is yeah, this would still be a miss, then it is a compulsory miss. But if it is a hit in your infinite cache but it is a miss in your given cache, then you will say, oh well, this miss would not have happened in an infinite cache, and therefore the problem here is smaller cache capacity. Now let's say you had large enough cache, right? What else could go wrong? Well, we talked about how fully associative caches are expensive in terms of area, as well as takes longer to do all those comparisons that you need to do. So then we talked about a direct mapped cache and two-way or three or four-way set associative caches, right? Now, because of the diminished degree of associativity, you may have some cache misses. So the example that we have been talking about is, let's say you have a direct mapped cache, and let's say the blocks A and B happen to map to the same cache line. And so if they are accessed alternatively, we said, well, A and B would kick each other out from the cache. As a result, you may end up with a cache hit rate of 0%. And the reason why we are incurring all these cache misses is not necessarily because of lack of cache capacity. It might very well be the case that you had enough cache capacity where you had plenty of these cache lines sitting around, but they're not being utilized. But the cache blocks A and B happen to map to the same cache line and conflict with each other, right? And so the way to reduce those conflict misses is to try and map these cache, try and provide more either try and map these two blocks to different cache lines, which means that maybe you need to increase the cache size, and that way you would be able to reduce the conflicts that may happen. But more importantly, you probably want to provision more ways so that A and B can be simultaneously be stored in the cache. So if you are given a cache and you ran a program and you observed some cache misses, and if for a equivalent fully associative cache of the same size, if those misses would not have happened, then you can say that those misses in your given cache is due to conflict misses. So now let's say I give you a cache. Let's say I'm going to call this as a given cache. So I'm going to call this as a 370 cache, just so that we can remember what we're talking about. So I've designed a cache in my class, and I'm going to run my program, and I'm going to observe a certain cache hit and miss pattern, right? So let's say I have addresses A1, A2, A3, and so forth. So I'm running my program. This is my sequence of addresses, and when I ran it on this cache, I observed that some of these are misses and some of them are hits. And now I ask myself this question: what is the type of these misses? How do I go about answering that question? Well, to answer that question, you need to simulate two more caches. One is an infinite cache that has the same block size as your 370 cache, and then a fully associative cache with the same cache size as your 370 cache. So let's say the size is S for the 370 cache, the size is S for the fully associative cache. Let's say the block size is B for your 370 cache, the block size is B for the fully associative cache. For the infinite cache, again the block size should be B, but obviously it's an infinite cache, so there is no size restriction. Okay, so I would go and simulate these three caches for exactly the same address pattern that we have here, and then observe whether these accesses are going to be hits or misses. And let's say I observe that the access to the address A1 is a miss in the infinite cache. Then I can confidently say that this miss is not because of lack of capacity. It's not because due to lack of associativity. It's simply because it's a compulsory miss, meaning this is the first time I'm accessing this cache block. And so then if I observe a miss in the infinite cache, I'm going to classify those as compulsory misses. So miss in an infinite cache would be classified as a compulsory miss. And then I go and simulate my fully associative cache. Let's say there was a memory access which was a hit. Let's say this is my infinite cache and this is my 370 cache. So let's say there is a hit in the infinite cache. But then when I simulated my fully associative cache, it turned out to be a miss. So what does that say? Well, it says that this miss is not really due to lack of associativity because we are simulating a fully associative cache, but it should be because of lack of size. And so any miss that is observed in the fully associative cache of the same size as your 370 cache, I'm going to call it as it has to be due to lack of capacity. So therefore, we are going to classify that as a capacity miss. So and finally, any miss that you observed only in your 370 cache, but if it was a hit in both infinite cache and a fully associative cache, would be classified as a conflict miss. So to summarize, to classify the misses observed for a given cache, you need to simulate two other fake caches. One with the infinite capacity but with the same block size. Another which is fully associative but it has the same cache size and same block size as your given 370 cache. and then I simulate the caches, these 3 caches, for the same address pattern. And any miss that I observe in the infinite cache is going to be classified as a compulsory miss. And of the remaining misses that you observe in the 370 cache, any miss that I observe in the fully associative cache would be a capacity miss. And of the remaining cache misses observed in the 370 cache, those will be classified as a conflict miss. So I would have to choose this specific order when I try to classify a miss into one of these 3 categories. Okay, let's now look at a simple example to understand how to classify misses observed for a particular address pattern. So I'm going to design a cache. So let's say this is my 370 cache, EEX370 cache. It's a cache of size 64 bytes, and it has a block size of 16 bytes, which means that the number of blocks in the cache is 64 divided by 16, so it's 4 blocks. And it's a 2-way set associative cache. So what that means is I would take a 16-bit address that is given to be the size of my address, and the block size is 16 bytes, so that means 4 bits for my block offset. And then it's a 2-way set associative cache, so that means the number of sets is going to be the number of blocks or number of lines divided by the number of ways, which is 2. So the number of sets is going to be 2 sets. So to figure out which set I should go to, I just need 1 bit, and the remaining 16 bits is going to be tags. So 16 minus 1 minus 4, so that is 16 minus 5, that is 11. So this is my set index, and this is my tag. So I'm asked to classify this address sequence into the 3 categories that we just spoke about. So remember, when I said that in order to classify, first I need to simulate 3 different caches: infinite cache, a fully associative cache, and then the given cache. So let's start with simulating an infinite cache. Now, in the case of an infinite cache, the only restriction that you derive from the problem statement is the size of your block offset. So the block offset or the block size does not change across any of your 3 caches. So the block offset size was 4 bits. The block size was 16 bytes, and so therefore the block offset was 4 bits. So what I have done here is this is a hexadecimal, and so I have partitioned the address into 2 parts, and so this is 4 bits in hexadecimal, so I have kept that separate, and what you're left with here is your tag in your infinite fully associative cache. So the infinite cache is also assumed to be fully associative. It doesn't really matter because you're never going to evict anything out of this infinite cache anyway. All right, so now let's see what cache hits and misses that you will observe in this case. So the first axis, so these are going to be your tags, so I can pretty much ignore my block offset when I'm simulating the cache, right? Because the hit or miss would primarily depend upon the tag and the set index. Block offset has nothing to do with cache hit or miss. So the tag is 0. This is the first time let's say that I have an infinite cache that I can put these tags into. So I'm going to add 0 to my cache. It's going to be a miss, of course, because this is the first time I'm accessing it. So this means this is a compulsory miss. And then I have a block with the tag 1. Again, it's a compulsory miss. Block with the tag 2. again it's a compulsory miss. Then block with the tag 0, which we have accessed before, so therefore this is a hit. Block with the tag 3, first time, compulsory miss. Block with the tag 4, again first time, compulsory miss. Block with the tag 1, we already have it in my infinite cache, so it's a hit. Block with tag 2, I do have it in my infinite cache, so it's a hit. Block 0, I do have it in my infinite cache, hit. Block 4, I have it in my infinite cache, so it's a hit. So I have a total of 1, 2, 3, 4, 5. 5 misses, and all 5 of these are later going to be classified as compulsory misses, because even in an infinite cache I endured them, and therefore the only way you could have solved it is by increasing the cache block size, but we are not going to do that. Alright, so now let's try to simulate a fully associative cache. So the fully associative cache has two restrictions from the problem. So one is the size has to be same as the given problem. So the problem said the cache size is 64 bytes, and we figured out that the number of blocks is 4. So my fully associative cache is going to have 4 blocks, and I'm going to try and simulate my address sequence. And you should assume a replacement policy. I'm going to typically assume a LRU policy for such problems. Now there is a tag array and a data array, which is what we have seen a cache to be architected with, but for such problems the data doesn't really impact whether it is going to be a cache hit or a miss. So it's not really necessary for me to keep track of the tag. In fact, the problems don't even tell me what the data part is. So I can simply ignore this part. I'm going to delete it so that it's clear what I'm simulating, so that it's not cluttered. So the tag is the only thing I care about when it comes to simulating a cache, especially a fully associative cache. Alright, so now I have the tag, and the block offset again doesn't change because it's same as what we had before. Now I have the same set of tags which we used in the infinite cache simulation. So now, because my capacity is finite, I have to keep track of my LRU rank, because it might turn out to be the case that I run out of capacity and I need to evict a cache block, and when I have to evict a cache block, I have to pick the one that is least recently used. So I'm going to keep track of my LRU rank along with the tag that is in the cache. Okay, so my address, I access my address 0, and then that is going to be a miss. Address 1, it's going to be a miss. Sorry, the tag is 2, again it's going to be a miss. Now the LRU ranks would have been, this is my most recently used, and tag 0 is my least recently used tag. So now I'm going to access tag 0 again. It's going to be a hit. So I'm going to update my LRU rank to be 0. I'm going to increment them by 1. I'm accessing address tag 3. It's a miss. Tag 4. Now when I access tag 3, this would have been 0, and these have to be updated. Okay, so now I have to bring in tag 4. It's not there in the cache, it's a miss. I have to evict the LRU, so LRU is going to be 3, so I evict this one, replace it with 4, and set its LRU rank to 0, and increment everyone else's rank by 1. Okay, right, so now I have access to 1. Unfortunately, we just kicked this tag out, so it's going to be a miss. Right, so now I have to kick someone else out to bring in this block. So the LRU is going to be this tag 2, so I'm going to replace this with tag 1 and reset this LRU rank to 0, increment everyone else by 1, Okay, now I have address tag 2. We just kicked it out, so therefore it is again going to be a miss. So I need to find a victim. The victim is going to be the least recently used, which turns out to be this block over here. So I replace this one with address 0, and the rank is going to be 0. Increment everyone else's rank by 1. So this is also going to be a miss. And then finally I have access to 4. So in this case I would access the tag and then compare it, and then I will see that it is actually a hit. Okay, so now we finished simulating a fully associative cache, and you'll notice that compared to my infinite cache, I encountered a few more cache misses. So so you'll notice that so now we have finished simulating a fully associative cache. You might have noticed that I encountered a few more misses than I did with my infinite cache. And those cache misses are going to be classified as capacity misses, because the only reason why we encountered those misses is not due to lack of associativity, but really due to lack of capacity. So we'll see which ones are those misses later on, but let's move ahead and simulate the given cache. The given cache, we're calling that as this EX370 cache. So again, I have partitioned the addresses into the block offset and the tag, the block offset and the remaining part. But in this case, I need to compute the set index along with the tag. Because I have two sets, one bit is going to be for set index. So I have to take each one of these, this part of the address, and convert them into tag and set index, where I extract one bit and keep that as a set index. So 0, the last bit, I'm going to write a 3-bit binary number. So 001, 000, 000, 001, 01. Okay, so now that we have the bits written in binary, so now we have the binary addresses for this part. We can now identify the set index, which is the last bit, and the remaining would be the tag. So we don't really need to worry about the block offset when it comes to cache simulation. So the way that I have represented my cache set is I have the data part. Again, you don't really need to simulate the data. It's only the tags that matter. And I have two cache blocks per set, so I need to keep track of which one is least recently used. Okay, so let's start with the first one. I have the address 0. So the tag is going to be, set index is going to be 0, and it's not there in the cache, so I'm going to store it, mark it as a miss. I'm going to mark the LRU bit with this L bit, so the L bit is the least recently used. Now my next address is set index is 1 and the tag is 0, so again I'm going to repeat my exercise here, mark it as a miss. Then I have a set index 0, tag 1. Unfortunately I have a space here, so I can store my tag here, mark my LRU bit to be the other one, but this is still a miss. Now I have the set index 0 accessing the tag 0. So set index 0, tag 0, it is going to be a hit, and I'm going to update my LRU bit. My next address is 3, 8, and we have set the set index is 1, tag is 1. I don't have it in the cache, so I'm going to move it to the cache and set my LRU bit accordingly. My next address is 4, set index is 0, tag is 2. It's not there in the cache, so I need to bring it. I need to evict least recently used block in order to do that. So the tag is 2. So this is the least recently used block, so I will replace it with 2 and update my LRU bit to be this. So therefore this is going to be a miss as well. The next address is 1, so this maps to set 1 and tag 0. So set 1, tag 0, it's a hit. I just need to update my LRU bit. Next address is 2, set 0, tag 1, set 0. Unfortunately, we don't have the tag because we had evicted it to make space for this tag 2, and so it's going to be a miss. But we need to bring it into the cache, so I'm going to evict this least recently used block and store the new one and update my LRU bit. And my next address is 0, so 0 cache set. I'm going to try and access my tag 0. Unfortunately, it's again a miss, and I need to evict my least recently used block and update my LRU bit, and so it's a miss. And the last one, again cache set is 0, and I want to access the tag 2. I don't have it, so it's going to be again a miss. So the LRU bit is going to be updated, the tag is going to be updated with 2. So as you can see, we'll see a bit later when we compile all of these miss sequences together that we encountered a few more misses than we did in the case of a fully associative cache. So those misses are going to be flagged as conflict misses, because the only reason why we encountered a miss in a set associative cache but we didn't encounter in a fully associative cache is because of lack of sufficient associativity. Okay, so what I have done in this table here is I've taken all the results from your cache simulation and tabulated them. And now we are going to go through this table and classify a miss as into one of these 3 types. So the first thing to do is the easiest part, which is to look at the misses encountered in the infinite cache. Now if there is a miss in the infinite cache, that means no amount of associativity or capacity is going to solve the problem for you, because it's a compulsory miss. So any miss in the infinite cache is going to be marked as a compulsory miss. I'm just going to call it as a comp, short for compulsory. So any miss that I see, which is 1, 2, 3, 4, 5, so those are going to be marked as compulsory misses. Okay, so my next step is to go and figure out the set of capacity misses. So capacity miss is one that I encountered in the fully associative cache of the same size as my given cache. Right, so this is my 370 given cache. This is fully associative cache. So I do have 1, 2, 3 extra misses compared to the ones that we have already flagged as compulsory. So this is taken care of, this is taken care of, right? because these misses have been taken care of because we flagged them as compulsory. So only 3 extra misses remain, and those need to be flagged as capacity misses. Okay, and the final one is to observe any misses that you may have encountered in the given cache which has not yet been flagged. So all of these have been flagged, and except this one, so that has to be classified as a conflict miss. So you'll notice something strange. You'll notice that if you notice this address, it turned out that it was a hit in the set associative cache, my given cache, but it was actually a miss in the fully associative cache. Now this strange phenomena happens once in a while, illustrating the fact that a set associative cache can actually have lower cache misses than a fully associative cache. Now the reason for this dynamics is because of the replacement policy not being perfect, right? So for the fully associative cache, we used the least recently used policy, and we know that it's just a heuristic, it's not meant to be perfect. And so it so happens that the set associative cache accidentally, or rather luckily, separated out conflicting cache blocks and managed to turn this particular access into a hit. So that can happen, and keep in mind that our goal is to really classify the misses in the given cache into these 3 types. And so given the fact that this one is actually a hit and not a miss, we don't really care about this, so this is not applicable. And this one is also a hit, so therefore that's not applicable. So our end goal is to classify the misses in the given cache into one of these 3 types, and the reason why we simulated these 2 is so that we can classify these misses into one of these 3 types. Okay. So like often it is the case with computer system design, in particular processor design, cache design is no different in terms of trade-offs. So we have gone through a number of design parameters like cache sizes, block size, associativity, replacement policy. So the question is, what is the right answer for these choices? And the answer often depends upon your target applications that you would like to run and the technology, the processor technology that you're trying to leverage. Processor's clock frequency, how long does it take to go to the main memory, etc., etc. So there's no one right answer for these parameters, but we can come up with a set of design principles that would govern how to choose them. So let's start with some simple questions. Can the block size be not power of 2? Can number of sets be not power of 2? So if you recollect, the way that we define block size impacts the number of bits that we would use in the address. So it is therefore natural to assume that the block size and the number of sets would be a power of 2 because we are going to use X number of bits from the address. And so if you're going to use X number of bits, then you want the number of bytes in the block or the number of sets to be 2 to the power of X bits. Now, the next question is, can the number of ways in a set associative cache be not a power of 2? Though it's uncommon, it is not impossible to design a 3-way set associative cache or a 5-way set associative cache. The way to think about it is, if I had a set number of cache, let's say if I had like 4 sets, which means that I would have defined the number of bits in the set index, right, to be 2. So I would already choose one of these 4 cache sets from the address. Now it's up to me to define how many blocks I want to store in these sets. And it's quite okay to store 3 blocks per set, because then you just need to configure the number of tag comparisons to be 3, right? So it is therefore possible to define set associativity to be not a power of 2, as it doesn't really impact the way that we would configure the caches in terms of utilizing the number of bits and so on and so forth. But oftentimes cache geometry matters when you lay out these structures in a processor chip, and symmetry helps. And with an odd number, symmetry is very hard to achieve. So that's one of the reasons why there is a natural tendency to go for 2 to the power of n associative caches. But it's not rare to see. It is not impossible to implement other types of set associative caches if need be. So I talked about trade-offs. So one of the trade-offs that we have to make is deciding the cache size. So obviously in a processor you have only a limited number of transistors at your disposal. Do you decide to spend them all on caches, or do you reserve them for some other structures, let's say larger branch predictor, right, etc. And so one has to decide what is the cache size that is beneficial to a program. And so you can take a representative set of programs and simulate a variety of cache sizes and observe the hit rate. So what you see is a graph like a simplistic graph that I have shown on the picture here. So you vary the cache size, and then for the applications that you're interested in, you observe the cache hit rate, and then often you'll notice that the curve kind of plateaus out, right? There is an inflection point at which increasing the cache size beyond that point doesn't really help you much. And oftentimes this is the size of the working set of the program that you're analyzing. So working set of a program is the total size of the data that a program accesses in a given time interval, right? And so that obviously is a fuzzy definition, because what should be your interval length? Do you consider 1 second to be an interval or 10 seconds to be an interval? Nevertheless, it's a useful definition, and you can vary the interval length and observe this phenomenon. So if I can draw a graph like this, then I can say, okay, my cache size should really be at the knee of the curve. Now, one downside of having larger caches is I would be investing transistors into that structure, so there is an opportunity cost there. I can take those transistors and use for some other structures like branch predictor, like I was saying. The other issue with larger caches is that it can increase the latency, because if your cache is larger, then you need larger decoders, you need longer wires to get to the data, etc. So the access time of a larger cache is going to be higher than a smaller cache. So we talked about this when we talked about the memory hierarchy. And so oftentimes in modern processors, you have multiple levels of caches to overcome this size versus latency trade-off, where you have this really small but very fast L1 cache, and much larger but slower L2, and then even larger and even slower L3 cache. The second trade-off is the block size. Now, the advantage of a larger block size should be clear now. It's essentially that you will be able to exploit better spatial locality. So if I vary the block size, then you can expect to observe a higher cache hit rate, because you are you're exploiting more and more spatial locality. But after a point, your program may not have a sufficient spatial locality to yield better hit rates, right? And so in fact, you may start observing a decrease in the cache hit rate. Why is that? Well, if I bring a very large cache block into my cache, then I may not utilize all the data before I evict that cache block out. So if you assume that the cache size is a constant, and if you divide up that cache into really large chunks, let's say 2 big chunks, and if I access an address X and you bring in a big chunk of data and you fill it up with this one big chunk, and if I don't really access most of it, right, then I have polluted my cache with all this useless data which I'm never going to access. So you're reducing the effective capacity of your cache by increasing the cache block size, and that's why you see a decrease in the cache hit rate. The other disadvantage of a very large cache block is you may end up consuming extra memory bandwidth. Like I said, you bring in this big cache block from your memory into your cache, and you don't really use all of it, which means that you have consumed your memory bandwidth without really turning it into good use. So the lot of useless data transferred result in wasted memory bandwidth. So finally, we talked about associativity today, where higher associativity reduces the conflict misses, and so you can increase the cache hit rate. Obviously, it's beneficial from that perspective. But again, just like in the case of cache size and block size, there is a law of diminishing return that kicks in, where the cache hit rate stops increasing. It doesn't decrease as badly as we witnessed for block size, because there you're actually polluting the cache. But here, if you just have higher associativity, it just means that you need to do more tag comparisons, and so you may be expending more energy doing those comparisons, but the cache hit rate may not decrease. So smaller associativity means that you would have lower cost because you need to have fewer comparators to do those tag comparisons, and because you need to do fewer comparisons, your access time can also be faster. So again, there is a trade-off between larger associativity yielding higher cache hit rate, but at the same time increasing your cost and latency of your access. And we talked about the fact that associativity need not be a power of 2.